The normal distribution, commonly known as the bell curve, is a fundamental concept in biostatistics. It underpins many analytical methods, helping researchers estimate the range in which the true population values are likely to fall based on a sample data. To better understand how normal distribution works, let's first explore a simple example. Suppose you toss a coin 10 times. Since each toss has a 50% chance of landing heads, you'd naturally expect to get about 5 heads. But what if we repeat this coin tossing experiment multiple times? Would we always get exactly 5 heads? Let's find out. Imagine repeating this experiment, each consisting of 10 coin tosses 100 times. Each set of 10 tosses might produce slightly different outcomes. Sometimes exactly 5, sometimes 6, sometimes 4, or even fewer. What happens if we carefully examine the results? However, if we plot the outcomes on a graph showing how frequently we get exactly 5 heads or slightly fewer like 4 or slightly more like 6, a familiar shape emerges, the bell curve. Here is why. The most common results, exactly 5 heads, forms the tallest peak at the center. Slightly less common outcomes such as 4 or 6 heads form smaller bars on either side of this peak. Even less frequent results, 3 or 7 heads, appear as progressively shorter bars farther from the center. This tapering effect visually illustrates the key finding behind the normal distribution. Most outcomes cluster around the average, with fewer occurrences as you move away from the central point. The concept of normal distribution is especially important when we are trying to estimate unknown population values, such as population mean, from a limited sample data. For example, suppose we randomly select 100 individuals from a large population and measure their systolic blood pressure. Let's say the average systolic blood pressure in this first sample is 140 millimeters of mercury. In practice, we typically conduct such studies only once, but imagine repeating this sample experiment multiple times. In the second random sample of 100 different individuals from the same population, the average systolic blood pressure maybe say 150 millimeters of mercury. Right? We repeat this experiment third time, and we enroll another 100 individuals from the same population, and this time we might get mean systolic blood pressure of these third group of individuals as 160 millimeters of mercury. We repeat it fourth time, we get a mean systolic blood pressure of 110, and then 170, and so on. So if we continue repeating this process and plotting each of these samples' averages on a graph, a pattern will start to emerge. These sample means naturally form a normal distribution. Importantly, the sample averages closer to the true unknown population mean occurs more frequently, while those farther away appear less often. In fact, because of the properties of normal distribution, we can confidently say that about 95% of these sample averages will fall within 2 standard deviations of actual population mean, as we will see shortly. So this powerful characteristics allow researchers to make accurate and reliable predictions about entire population when working with a limited sample data. The phenomena we just explored forms the basis of what we call the central limit theorem, or CLT, which states that the distribution of the sample mean from a large number of independent, identically distributed samples approaches a normal distribution regardless of the original distribution. In simpler terms, even if the data we start with aren't normally distributed, when we repeatedly take samples and calculate their averages, these sample means naturally form a bell curve. In our later videos, we will demonstrate practically how the CLT works. Now that we have explored the normal distribution, let's summarize the key characteristics of a perfectly normal distribution that we call the standard normal distribution. First, in the standard normal distribution, the mean, median, and mode all align exactly at the center. This illustrates the symmetry and balanced shape of the distribution. Secondly, the normal distribution follows a very useful guideline known as 68, 95, 99% rule, 99.7% rule. This rule tells us that approximately 68% of data values lie within one standard deviation of the mean, about 95% lie within two standard deviations, and nearly all, around 99.7%, lie within three standard deviations. This principle helps researchers quickly interpret and understand their data, as we will illustrate with practical examples in the next video. See you in the next lecture.